Hi, this is Dr. Randy Papke, and it's time to learn all about the chemical context of life. We're going to do Chapter 2. So to go ahead and get started on that, we're just going to look at the overview first. The thing about, I know you're in biology class, and the thing about biology is that it's a very interdisciplinary field. Chemistry is essential to understanding biology. So what we're going to do today is we're going to learn some of the basics about chemicals and understand how those relate to the biology of our living things. And we're also going to be learning a little bit about water because that is a chemical very important to life. So the first concept, pretty straightforward. Organisms are composed of matter. And matter is anything that takes up space. I grabbed this image off the internet. It talks about different states of matter, solid, liquid, gas. I think most of us are familiar with those different states of matter. But the thing is, all living things are composed of matter. That's the main idea here. Now, matter itself is made up of elements, and elements are defined as any substance that cannot be broken down to another substance by a chemical reaction. We think about these as pure substances. They are the basic elements of life. So a compound is different from an element. A compound is a substance that has two or more elements together in a fixed ratio. It turns out that when you mix elements into this fixed ratio and they interact with each other to form compounds, those compounds have emergent properties. Emergent properties just means that they have properties that the original elements did not have. They're different from those elements. A great example can be seen in sodium chloride. Sodium chloride is a compound made of two elements, sodium and chlorine. And when you mix them together, you get sodium chloride. Sodium is a solid element, and chlorine is usually found in a gas form. But, here's something interesting, is that both sodium by itself and chlorine by itself are very dangerous. But when you mix them together into this fixed ratio of sodium chloride, you get something that's actually necessary for life to occur. There are 92 natural elements found in the universe, some more man-made ones, but we're not going to go into those. Of those 92 natural elements, about 20 to 25% are considered essential elements. They're absolutely needed by living things in order to be alive and be healthy and to reproduce. You can see a list of some of the most important essential elements here in this table. And on this table, you can see ones that you're very familiar with. There's oxygen and carbon and hydrogen. And of those three, they make up 96.3% of your body mass. That's incredible. That's a lot of oxygen, carbon, and hydrogen. There's other ones that are also essential elements, including nitrogen, calcium. You've heard of these probably, phosphorus, potassium, sulfur. Here's sodium and chlorine at a very small amount, but if you don't have them, you will not be able to live. And also magnesium. All of these together are considered essential elements. There are some other elements called trace elements, and those are only in very small or minute quantities. And a good example for you is iodine. In vertebrates, that's anything with a backbone, vertebrates, iodine is absolutely necessary for the thyroid gland to work properly, and the thyroid gland is very important in your metabolism. If you lack iodine, then you can get a disease called goiter, and definitely do not want to have goiter. It's very uncomfortable and painful, and it's a swelling of the thyroid gland, large lump in your neck. That's one of the reasons why they put iodine in table salt. So some naturally occurring elements are quite toxic to humans, and an example of one is arsenic. Arsenic is found linked in many diseases. Also, if taken in high enough quantities, can be deadly. So very interesting. Some plants have evolved the ability to absorb toxic elements. And an example of this is the sunflower. Sunflowers are amazing plants. Besides providing seeds to eat for the birds and for the humans, sunflower plants can take up lead. Remember how bad lead is for you if you just think about what's happening in Flint, Michigan. You do not want to be ingesting lead. It can damage your brain. Also, zinc in high quantities can be very damaging to you. Other heavy metals like mercury, those kinds of things that are in high concentrations can be deadly. Sunflowers can absorb them and take them out of the soil. So an example of this is that they planted sunflowers after Hurricane Katrina, and that was used to detoxify the soils that had been contaminated by all of the mess that happened after that hurricane. The next thing we're going to talk about is the structure of atoms, and every element is made up of a specific type of atom, and those atoms are different from the atoms found in other elements. So an atom is defined as the smallest unit of matter that still retains the properties of the element. You can see here a classic image of an atom with the electrons going around the center. And we'll talk a little bit more about that on the next slide, which is what are those particles that make up the atom. We call those subatomic particles. So atoms are composed of these subatomic particles. You might have heard of them. There's the neutron and the proton. Those are both found inside this region called the nucleus. And the neutron has no electrical charge. Protons have a positive electrical charge. And electrons, which are found outside, going around the outside of the nucleus, those have a negative electrical charge. If we look at a helium atom, and you can see one right here, there's two different versions. They're both helium atoms. You can see here that the neutrons and protons form this thing called the atomic nucleus, and then the electrons are kind of in this cloud all the way around. This is actually a fairly good diagram of what they look like, but we like to simplify the way the electrons are kind of graphed around a nucleus, so we often put them as rings around the nucleus. But again, they form more of a cloud than a ring. So remember, electrons are negative and protons are positive, and neutrons are neutral. If we're trying to think about the mass of an atom, remember we were just talking about mass, then what we're going to talk about is how many protons and neutrons are in the nucleus. If you add those two up, it's basically, you're talking about mass, and mass of atoms are measured in daltons. So again, same image that we saw before, but going into a little bit more detail. For example, atoms in your various elements, right? They have different numbers of protons, neutrons, and electrons. And we have words to describe those things. So if we give all elements a number, and the atomic number is the same number as the number of protons in the nucleus. So if we look at this diagram right here, we can figure out the atomic number is the number of protons. So the atomic number of this atom is 1, 2, 3, 4. So this is atomic number 4. The element's mass number is the sum of protons plus neutrons. So we're going to add up the protons and the neutrons. And in this particular atom, we could say the mass number is 1, 2, 3, 4, 5, 6, 7. So that's the mass number. We tend not to think about the mass of individual atoms in this class. We tend to think about more of the mass number in terms of the element, and we'll explain a little bit more about that later. But in general, the atomic mass is the atom's total mass, and you can approximate it by the mass number. So if we're looking at protons and neutrons, and each of them have a mass of 1 Dalton, then you can estimate the atomic mass by adding up the number of protons and neutrons. I'm going to step through this with you. So this is an example right here of something that you might see in a periodic table or some symbols associated with Na, that's sodium. Remember, we saw sodium earlier. So on this particular version, what we're seeing is up top here, we're seeing the mass number. Remember that the mass number is the number of protons plus neutrons. And right here, we're seeing the atomic number. The mass number is always equal to or greater than the atomic number. So whatever the bigger number is, and they can flip-flop positions depending on what periodic table you're looking at. Whatever the bigger number is, that's the mass number, and the smaller number is the atomic number. The atomic number is the number of protons, and if your atom is neutral, it's also equal to the number of electrons. So in sodium, the atomic number is 11. That means there's 11 protons. If you've got a neutral sodium atom, it's also got 11 electrons, and its atomic number is 11. If you want to figure out how many neutrons there are, though, notice that's not here. This number is protons plus neutrons. This is just protons. So we're going to do some subtraction. 23 minus 11. If we do that, if we subtract the mass number, if we take the mass number and subtract the atomic number, for sodium it's 23 minus 11, we get 12. And that means that there are 12 neutrons in the sodium atom. When you look at a periodic table, you often see the atomic number on the top, a symbol in the middle, and the mass number on the bottom. So just kind of keep that in mind. The way I showed it to you earlier here, that's not always the way that you see it. Sometimes you see those numbers flip-flopped around. So just kind of keep that in mind. When you're looking at atoms, it's important to understand that not all atoms of the same element have the same number of neutrons. So if you have an atom, if you have a couple atoms, and they have the same number of protons, because that's how we define atoms, right? The atomic number is the element, and that's how many protons they have. They could have a different number of neutrons. The word we use for that is isotope. Again, an isotope is defined as two atomic forms of an element that differ in the number of neutrons. So if you look over here, you can see there are 3 isotopes for carbon. There's carbon 12, and I didn't grab 12 there, but it's carbon 12. Carbon, that's your most abundant type of carbon. It has 6 protons and 6 neutrons. So our mass number is 12. However, there is an isotope, and this is called carbon 13. And so that has 6 protons but 7 neutrons. Notice that the number of protons are exactly the same. Carbon 14 has 6 protons and 8 neutrons. It has a mass number of 6 plus 8, or 14. And you can see those calculations down here. Of these 3 isotopes, carbon 14 is actually a radioactive isotope. It doesn't stay stable as carbon 14. In fact, it decays spontaneously. And as it decays, it gives off these particles and it gives off energy. And that energy is what we think of as being radioactive. It's literally giving off energy. Carbon has an average mass of 12 daltons. But again, specific isotopes have different masses. So if we're looking at one of those isotopes, one of those less common isotopes, you write it like this, 14C, but you call it carbon 14. Notice that this looks really similar to what appears on the periodic table, but when it's just that superscript there and it's written in front of the symbol, it's talking about the isotope. Isotopes are really important for understanding life. For example here, that we'll go through a couple of examples really quickly, but we use radioactive isotopes to date fossils. Carbon 14 is an example of one that we use quite a lot in dating our fossils. We can also use them as atoms to travel through your body and figure out what metabolic processes are going awry. So we can use these for finding specific cancers. We can use them to find out if you have your thyroid gland is too active or not active enough, and so they're very, very useful. Luckily, a lot of the radioactive isotopes that we use to help figure out our medical issues they decay really quickly, so they're not harmful. But most isotopes that exist out there in the world have a long decay time, and they are quite harmful to humans and other organisms because they damage the cells. So we need to think about energy. Biology is also focused a lot on energy, and we define energy as the capacity to cause change. That means if something is able to change something else, that thing has energy. Potential energy is energy that all matter has simply because of where it's located or the structure that it has. So we'll talk a bit more about potential energy in a little while. Just something to keep in mind, keep that term in mind. But one of the things that's really important is when we're thinking about potential energy and electrons. Electrons are the main form of potential energy in an atom due to their distance from the nucleus. And we'll talk a little bit more about that as well. Anytime you have a change in potential energy, this is going to change in a very, very fixed amount. And so it's a very discrete packet of energy. And last but not least here, an electron's energy is related to its distance from the nucleus. So let's take a more concrete look at that energy. So we say that electrons are found in different shells, and this is the shells are the distance, the average distance from the nucleus. So you can see over here that there's a shell there, and there's a shell there, and that's a shell there. We say this is the first shell, the second shell, and the third shell. The closer you are to the nucleus, the less energy we say the electrons have. So this is the lowest energy shell, the second is the middle, and the third is the highest energy shell in this example. As energy of the shell can increase as that distance from the nucleus happens, and electrons can move between shells. So you can have a low energy electron jump to the third shell, and all of a sudden it has a lot of energy, and it's going to move to this higher energy shell from the lower energy shell by absorbing or releasing energy. So it's going to have to absorb energy in order to move up, and then if an electron is moving down the shells, it's going to actually lose energy or release energy. You can think about it kind of like this releasing energy is a ball kind of going down steps. So going down the steps releases energy, but moving up the steps actually takes energy. You got to push that up the steps. So atoms behave in very specific ways, mostly because of where the electrons are located in their shells. And we're going to take a quick look at a periodic table to see how those electrons are distributed in the shells for each element. Again, you're not going to have to memorize this, by the way. It's just something that you need to know the basics of. So here's hydrogen. It's got 1 electron. Its atomic number is 1, and that means it only has 1 proton and 0 neutrons. So there's that 1 little electron in that first shell. Helium has 2 electrons in that first shell. And as we go along, lithium has 3, beryllium has 4. Notice how those electrons are distributed. They start getting spread out along the second shell here. And as we go into the third shell with sodium, it's got 1 electron in that outer shell. Magnesium has 2 electrons in that outer shell, and so forth, all the way through. Here's chlorine with 7 electrons in that outer shell. 1, 2, 3, 4, 5, 6, 7. The outer shell can take a total of 8 electrons. The second shell can take a total of 8 electrons, and the inner shell can only take 2 electrons. chemicals behave differently depending on the number of electrons in the outermost shell. And we call the outermost shell, whether it's the first shell or the second level or the third level, whatever one's the outermost one, again, depending on the atom, it could be one shell or two shells or three shells. We call that the valence shell. So again, going back here, this is the first shell is the valence shell in hydrogen, but the second shell is the valence shell in lithium, and the third one is the valence in sodium. Any electron that's found in the valence shell is called a valence electron. And so atoms are reactive based on whether or not they have paired electrons in the valence shell. So going back here, you can see that, for example, argon with 8 electrons in its valence shell, it's not going to be reactive at all. All of them are paired up. But if we look over here at lithium, that doesn't have any pairs, and it is definitely very reactive. Beryllium is looking for pairs. A lot of these are looking for pairs for the outer shell. Nitrogen has 3 unpaired electrons, and carbon has 4 unpaired electrons. That becomes really important later as we're looking at chemical structures in the next chapter. So we're going to stop the video here and start part 2 in a second. I'll start a new video, and that'll make it easier for you to watch all these videos in little chunks. See you in a minute.